Dear students, today we shall study linear momentum, angular momentum, moment of inertia and torque. First, let us define linear momentum. Linear momentum is defined by this small p equal to m into v, where m is the mass of the particle and v is its velocity. And if the position vector of the particle is r, then we define angular momentum. By small l, which is small r cross p. That is the cross product of the displacement vector r and the linear momentum small p. We define now torque. If F is the force in rectilinear motion, means linear motion, then torque tau is defined by this cross product of the displacement vector and the force gives the torque acting on the particle. This angular momentum and torque, they are relevant to rotational bodies or rotational particles, and small p, the linear momentum, and force F, they are relevant to rectilinear motions, means linear motions. Now we discuss relation between torque and angular momentum. Okay, to find this relation, first we note that the we have the angular momentum small l equal to r cross p and tau equal to r cross f. If we differentiate small l, the angular momentum, we have dl by dt which can be written as, the for cross product here r cross p, here taking derivatives, we will have to remember the order of the vectors, so we'll have to keep the right order. Now we know dp by dt is the force. This is from second law, Newton's second law. The time derivative of linear momentum is the force, and the time derivative of displacement is the velocity, and p is m into v. Now if you apply this relation, tau equal to r cross f, so this is the torque tau, and you see the cross product of v with itself is 0. Thus we have found that the torque acting on a particle is just the time derivative of the angular momentum. So this time derivative of angular momentum is equal to the torque. This is the required relationship between the torque and the angular momentum. Okay, next we consider rotational kinetic energy of a rigid body. Also, kinetic energy of a rotational rigid body. If we if we draw a rigid body like this, and let us suppose that the rigid body is rotating about the axis AB. And this is the rotational axis. And we consider that the rotational axis passes through the rigid body through the point O. Now if we consider that the rigid body consists of many this kind of smaller particles, we consider three such particles. Let us suppose that this is the distance is r1 and the mass of the particle is m1, and this is say r2, mass of the particle is m2, this is r3, mass of the particle is m3, and so on. So the kinetic energy of the particle with mass m1 is T1 is half m v1 m1 v1 square. Similarly, T2 is half m2 v2 square. And T3 equal to half m3 v3 square, and so on. But we know the relation between angular velocity and linear velocity is this, where omega is the angular velocity and v is the linear velocity. R is the distance of the particle from the rotational axis. This is angular velocity, and v is the linear velocity. Actually the magnitude of the linear velocity. So if we apply this here, then we can write down T1 equal to half m1 and r1 omega whole square, which is half m1 r1 square omega square. Similar for the other particles, where omega is same for all the particles because the whole rigid body is rotating about the axis. Now we would like to write down the total kinetic energy of the whole rotating body is the sum of the kinetic energies of all the particles constituting the body. Similarly, you can write down for the particle with mass m2 is half m2 r2 square omega square, and half m3 r3 square omega square. Okay, and this sum can be simplified and can be written as this. take common half, we take common, then is m1 r1 square plus m2 r2 square m3 r3 square plus dot 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 and take common omega square. We write down this summation over mj rj square. This is omega square, where j runs 1 to the total number of particles. That means you start from j equal to 1 and then next term will be j equal to 2, so his first term is m1 r1 square plus the second term is m2 r2 square plus dot dot dot, like you'll have to continue for all the particles constituting the body. Now we would like to write down this expression as half I omega square. So this is the kinetic energy of the rotating body, and where I is the summation over j mj rj square. This is actually the moment of inertia of the body. Okay. Then how can we then define the moment of inertia of a body? We can define this as the sum of product of mass and the square of perpendicular distance of each particle consisting of a body or an object from a straight line. We call this straight line axis of rotation is called the moment of inertia of the object with respect to that straight line. We would now like to discuss about the relation between moment of inertia and angular momentum. To find this relation, we consider this okay, you know, the angular momentum is r cross p, where p is the linear momentum, and if the angle between the r vector and p vector is theta, then we can write down is this rp sine theta, and the unit vector is small n. In particular, if theta is 90 degree, we consider, then L can be written as RP, because sine 90 degree equal to 1. This one R and M into B, and this one give us the magnitude of the angular momentum is mvr. This is a special case when the angle between the displacement vector and the linear momentum is 90 degree. Now Now if we have a particle, we put the index j because we do not have a single particle for a rigid body, we have many particles. So for the jth particle we can write down this relation L equal to mvr as for the jth particle. We write down Lj equal to mj vj rj, but we know the vj equal to rj omega, so is mj rj omega and this is rj. We can write down mj rj square and then omega. And the total angular momentum then can be written as the summation over Lg. So we substitute the value of Lj is mj rj square omega, which can be written as this. But we know this is a moment of inertia I, so L, this is the total angular momentum of the rigid body. Of course, this is the magnitude of the total angular momentum. So we can write down is I omega. So you see the relationship between angular moment of inertia I and the angular momentum L. I should mention here that if we have continuous distribution of mass for distribution of mass of a rigid body, in the case of rotation, the moment of inertia, instead of this summation, this instead of this we will have to take the integration. Where dm is a small portion of the total mass of the rigid body at a distance small r from the rotational axis. Now an important quantity, and this is known as radius of gyration, we are going to define. This quantity will be needed later on. The definition of radius of gyration is if the total mass of a body can be concentrated at one point such that the moment of inertia of the concentrated mass with respect to an axis is equal to the moment of inertia of the total rigid body with respect to the same axis, then the perpendicular distance of the concentrated mass from that axis, that fixed axis, is called the radius of gyration. Okay, next we consider the impulse of force. So we define impulse of force in two cases. In the rectilinear motion, means linear motion, the impulse of force is defined by this. if a force acts for a time from ti to tf, then this integral defines the moment of force, or I'm sorry, impulse of force, or linear impulse of force. If the force is constant and does not depend on time, then the impulse of force can be written as this. You can bring f outside because it is constant, and then ti to tf dt, which can be written as where delta t is the time difference, tf minus ti. If it is not known how the applied force is changing, but we know the average force, say the average force is this, then this is average force, and then the average force, then the impulse of force will be this, average force into the time difference or time interval. We know from the second law of motion, F is dp by dt, and we can also write down the impulse of force as this, and this dt, and this we can write down pf minus pi. Then change in linear momentum. So the impulse of force can also be written as pf minus pi, which is equal to delta p. So change in linear momentum is the impulse of force. Now rotational impulse of force. In the case of rotational motion, the similar quantity to force is the torque. So the impulse of force in the case of rotational motion can be written as this, ti to tf and here tau dt. And if this tau is constant, if tau is constant in time, then we can bring the tau outside the integral sign, and the rotational impulse of force can be written as this. Again, in terms of angular momentum, this tau equal to dl by dt. We can write down the impulse of force in the case of rotational motion. Instead of tau, we put dl by dt. And this can be written as, so this is LF minus Li. That means change in angular momentum. Therefore, the impulse of force in the case of rotation is nothing but change in angular momentum. And previously we have found impulse of force in the case of rectilinear motion. This J equal to delta P, change in linear momentum gives the impulse of force in the case of rectilinear motion. Okay, next we shall consider conservation laws of linear momentum and angular momentum. This is the last topic of this lecture. Conservation of linear momentum. We know from the Newton's law that force is nothing but the time derivative of the linear momentum. If the force acting on a particle or system of particles is 0, then dp by dt equal to 0, which gives us the linear momentum is constant in time, and this is known as the conservation law of linear momentum. For a system. Similarly, we can have the conservation law of angular momentum. We know the torque acting on a particle or a system of particle. In the case of rotational motion, it is the time derivative of the angular momentum. Now, if the torque acting on the system is 0, then dl by dt equal to 0, which gives small l is constant in time, and this is known as the conservation law of angular momentum. Okay students, this is the end of today's lecture. In the next lecture we shall consider the concept of center of mass and the motion of center of mass of a system of particles.